Today we're going to be talking further about exponential and logarithmic modeling. Now we've already talked some about exponential modeling, in particular whenever you just maybe have a sort of basic exponential model, or you have some sort of initial starting amounts times some sort of growth to maybe like time or something like that. We've talked about whenever we've had this continuously compounding model, which you might have seen sometimes labeled as principal times e to the rate times time, or by just some sort of starting amount, e to the rate times time. And then today we might also sometimes relabel that rate in a way that you would see more often in a science class, where we're going to call it k. But this is really just relabeling what those variables are called. They function the same way though. We still, whatever number is hanging out front, that's still your initial starting amount. Whatever number is up here in the exponent, one of them will represent your continuous growth or decay, and the other one is going to represent time. And then we also saw what is specifically pretty much always used in the context of finance, of where you have some sort of principal, or again, you could relabel it as a starting amount that is compounded not continuously, but a certain number of times, a discrete number of times, such as like 4 times per year or something like that, and is growing or decaying by a particular rate. And these are really kind of the 3 big exponential models we've seen. But in the past, pretty much we only, set them equal to some sort of final amount. We would plug into each of these models and solve for the final amount. What's going to be different today is now maybe I can actually give you the final amount and you can solve for any of these other missing pieces. So I could give you y and you could solve for t. And the reason why we can now do this and we couldn't at the beginning is because we didn't know how to solve exponential equations until just recently. And now that we can solve exponential equations, we can solve for any particular missing piece in this puzzle. So without further ado, let's go ahead and get into this. So here, if we're going to be modeling exponential growth or decay, and in particular, this is continuous exponential growth or decay. By this continuous exponential growth and decay, what we mean is that it is continuously compounding. They don't always use the word compounding whenever they imply this, but this continuously compounding growth or decay, where again, kind of that principle or that starting point is sort of reevaluated every single millisecond in order to make it where, it's growing or decaying essentially more rapidly than if you just do a basic exponential model. And we looked at this in particular in the context of finance mostly. If you have something with continuously compounding interest, where effectively your bank account every single millisecond will be like re-evaluating what it's considering the principal that it will be recalculating that interest rate on. So it's a way of basically making more money, because instead of just always doing it on your starting amount, we're like recalculating that additional interest based on how much more money you've already accumulated in the bank because you've already earned more interest on it. This actually also happens in biology a lot too. And we're going to be looking at a lot of those models today. So in biology a lot, we also sort of see this phenomenon where, like with bacterial growth, for example, it may also be effectively continuously compounding, where effectively every single millisecond it will be growing more and more and more and more and more based on a larger amount of bacteria being in there in the first place. Or it might be decaying similarly, where it's like this domino effect of increased decay as well. If you're talking about, killing bacteria with some bleach or something like that, that might end up having this effect as well. The way you would know in the real world which one you're going to go with is you would collect some data and you would see which model fits best. The way that you learn how to do that is actually more in a statistics class, which I would encourage you to take. Here, we're going to base it on, we've already had some other scientists who have figured out which type of model makes the most sense, and then we're going to utilize that model, which is also done a lot in the real world. Some other scientists might have figured out which model you're going to use, and now you have to use it. And the way that you know that this is the model you want is you should be looking for this keyword continuous. And probably on an exam in particular, I would even use the full phrase continuously compounding to indicate that you want this model that has your initial amount, e to the kt. With this, often in the past, we saw it with initial amount e to the rt, or you might have seen the initial amount called p. But these are all just relabeling the same idea, with again the number in front of the e being your starting amount. Whatever e is being raised to, one of those numbers is going to be your rate of growth or decay, and the other one is going to be time. And it's going to be decaying in particular if that rate is negative, and it'll be growing if that rate is positive. And then this is exactly what it's re-emphasizing here. So just like we know exists on exponential functions, we're going to have a horizontal asymptote at y equals 0. We know we can plug in anything theoretically for t here, although you might argue, well, in reality, we kind of know implicitly for the domain. For time in particular, if we're considering that our input, it wouldn't make sense to plug in negatives. But if we're considering k, our growth rate or decay, to be our input, then our domain truly is negative infinity to infinity, because then negative numbers just mean that we're decaying. So here I would kind of put an asterisk to say it kind of depends on if you're considering time or growth rate to be the input. When typically we actually consider time to be the input, and then there's an implied domain where 0 would be the lower bound. Implied time is bigger than or equal to 0. For range, though, just mathematically, it's always 0 to infinity. And also kind of the implied thing, too, of like you couldn't have negative stuff as well. There is no x-intercept because that's how a exponential model works. Our y-intercept is always our starting point. And again, it's increasing if we have a positive growth rate and decreasing if we have a negative growth rate. So let's look at an example you might see in something like a biology or a chemistry class. So it says a population of bacteria doubles every hour. If the culture started with 10 bacteria, write the population as a function of time. So here I know that I'm going to be using the y is equal to a naught e to the kt because, and this is an example of where I would probably on a test give you a little bit more direction than they're giving you here. There would have to be something that sort of says that we know that this bacteria has continuous growth. And something like a doubling time, once you've worked with it enough in your biology or chemistry class, that it will be kind of implied. You should see on your homework and on any exams that will prompt you with something like, we're using a continuous growth model. And because it says as a function of time, I'm going to go ahead and kind of label that we're making a function for the ending amount as a function of time using this model. And now let's sort of figure out what information they gave us here. So in particular, they gave us that we have, actually backing up, let's think about how these points work here for x comma y. What's considered my x value here? My x value is considered time. Time is my input because it says function of time. So I'm not considering the rate to be the input, I'm considering time to be the input. What does y actually represent? That's the amount of bacteria, which in this case I've labeled as AT, although you also could label it as Y. So let's figure out if there's actually a couple of points they kind of gave us here. So if it says the culture started with 10 bacteria, what's actually the ordered pair that they gave us? They actually really gave us the ordered pair that when time is 0, bacteria is 10. And in particular, what does this ordered pair correspond to in my model? That's that A naught, that starting amount. So I'm going to go ahead and plug in that I know that starting amount is 10. What's another implied point they gave us here? They also said that it doubles every hour. So if it doubles every hour, After 1 hour, how much is there? There's 20. So now I can plug in this point. So I can plug in the AT, so in this case, this is really A1. The amount when time is 1 is 20. 10E, I don't know K, so I'm going to leave that blank. And time is 1. And now I can solve for K so that I can write my generic function. Because before, if I just have AT is equal to 10 times e to the kt, I really still need K if this is going to be just a function of time. So then I can plug in my known point of when time is 1, the amount of bacteria is 20, in order to solve for K. Now this just becomes a exponential equation that I can solve. So I first want to get rid of multiplying by 10 out front by dividing by 10 on both sides. 20 divided by 10 gives me 2. K times 1 is just K. And then what would be my last step? I would want to natural log both sides. When I natural log this right-hand side in particular, that makes the K move out front. So I have the natural log of 2 is equal to K times the natural log of E. And what is the natural log of E? That is 1, because natural log secretly has base E, and log base E of E is just 1. Anytime those match up, that's 1. So I just figured out K was the natural log of 2, so I can plug that back in. So the amount of bacteria as a function of time is equal to 10, my starting amount, E, to the natural log of 2 times T. And we would actually just leave it exactly like that. You would not be expected to do a decimal approximation unless it was asked for. And that is exactly what this model looks like here. So it's doubling every single hour. First hour, it's got, after 1 hour, it's got 20. It started with 10. After 2 hours, it's 40. After 3 hours, looks like it should be about 80, and I'm not writing my things straight here. After 3 hours, we have 80. After 4 hours, we have 160, so it's doubling every single hour. That's that continuous exponential growth. And again, we would have to have some way of knowing it was continuous exponential growth. We also could write an even more generic equation. So let's say I didn't even tell you exactly how much I started with. So I wanted to write something that was a function both of whatever my starting amount was and time. It still doubles every hour. So we have our final amount is equal to the initial amount, e to the kt. And I'm allowed to keep that as a naught. I'm allowed to keep that t, but I still need to somehow solve for k. So let's sort of think about what points we have here. When time is 0, how do I represent how much is there when time is 0? That's that a naught. And after 1 hour, how much do I have? Well, whatever a naught is, I have 2 times that. So let's actually just try plugging this in and see what happens. So we still have just a naught stays as is, and then I can plug in the point 2 times a naught is equal to a naught e to the k, and then time would be 1 at that point. And then what do you notice happens with these a naughts? Well, I could divide both sides by a naught. That makes 1, and that makes 1. So then I have 2 is equal to k e to the k times 1. I can still natural log both sides. That moves k times 1 out front, so natural log of 2 equals k times 1 is just k. Natural log of e. The natural log of e is still 1. And I still get k is equal to the natural log of 2. So what the literal starting amount was actually did not change how I ended up solving for k, which I actually think is kind of cool. We can do a similar idea with a half-life as well. So a half-life is, again, we're going to say that this is also modeled with, and I'm going to even throw in the word continuous exponential decay. And it's how long it takes for half of whatever you're talking about to be left. So in particular, this is a term used a lot in chemistry class whenever you're talking about what is the half-life of a particular element. So whenever it's decaying exponentially, after how long will there only be half of your amount of uranium left or something like that. And we could solve it a similar way. So if you think about at time 0, you have whatever your initial amount A0 is, then whatever amount of time it takes there to be 1/2 A0, that amount of time is considered your half-life. And then we could again kind of solve for K in a similar way from this point, because you would be like, oh, it actually doesn't super matter what the literal initial amount is, because I can divide both sides by that. And then I have 1/2 is equal to e to the kt. I would still natural log both sides. That would make that entire exponent move to the front, so the natural log of 1/2 is equal to k times t times the natural log of e, and the natural log of e is just 1. And then here, hopefully they either gave you what k was or what t was for that half-life to happen, and then you'd be able to solve for the other. So this would be an example where they actually do that. So it says the half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time and the starting amount A0. So let's just kind of reset that up from the beginning. So we know our final amount, and this, again, they would have to kind of prompt you is somehow with the continuously decaying exponential model. That would be explicitly given to you on a test. It's possible in a chemistry class or something you will use this so often that they will expect you to just know that's implied. Our starting amount, e to the kt. We're kind of implicitly given 2 points. One of them is 0, A0. What's the other one? So after 5,730 years, there will be 1/2 A0 left. So let's go ahead and plug that in. So 1/2 A0, with A0 just being whatever my starting amount is equal to A0 e to the k times 5,730. If you really hate just seeing the A0s in here, I will go ahead and tell you for these doubling time and half-life problems, you could make up a starting amount, and as long as you just kept going with it, you would still find this next step to be true and it won't affect your final math, because at this step you would still be dividing by whatever that starting amount is. Cancels out to make 1, cancels out to make 1. And at some point you're still going to be left with 1/2 is equal to e to the k times 5,730. Just whichever way kind of makes most sense to you. I think it is nice to get sort of comfortable with the idea that it's okay to divide by a variable, and that I don't actually care what the literal starting amount is. I can still divide by both sides by it, and I'm good. From this step, what would I want to do in order to continue to solve for k? I would still want to natural log both sides, because that's how I get these out of the exponent to move out front. So then I have natural log of 1/2 is equal to k times 5,730, natural log of e. The natural log of e is just 1. And then what would be my last step to get k by itself? I would divide by 5,730, divide by 5,730. And this whole big old fraction is what k is equal to. So my final model, I'm going to rewrite this with what k is equal to. So that's the amount at time t is whatever my initial amount is, e to the natural log of 1/2 over 5,730 times t. And actually I'm going to rewrite that just a little bit neater, because I think it's a little bit hard to read. So natural log of 1/2 over 5,730 times t. And that would be your final model to express how much carbon-14 is left. And you could plug in any starting amount at any time and know how much is left. We, of course, can still do this with the continuously compounding interest that we looked at a lot in the past, which has the same sort of stem of a model. So for this one, we invested $1,000 and now have $10,000 at the end of some amount of time on an investment account that compounds continuously. So that's, again, that like kind of key word that tells you this is the model we want, with a typical annual return of 7%. For how long did you invest? So here we again kind of want to look at what were the implied points they gave us. So here we still have if time is the input and our money is the output now. One point they gave us was at time 0, I have 1,000 in my bank account. And then the other one is after some amount of time, I have 10,000 in my bank account. So here, this is actually what I'm missing, is that time. So if I'm plugging into this function, where now the amount is not talking about bacteria or about carbon or whatever, it's now talking about money. I have $10,000 when I started with $1,000. And now this time they gave me the rate, and we're going to keep it as a positive because it's I'm gaining money. It's not that the bank is taking away money from me, times time. And now I'm going to solve for time with a very similar method. So as my same initial first step, I want to divide by whatever's in front. Divide by 1,000. Divide by 1,000. 10,000 divided by 1,000. Looks like that leaves me with 10. It's equal to E to the 0.07 times T. What would be my next step? Still want to natural log both sides. So the natural log of 10, these numbers move out front, is equal to 0.07 T times the natural log of E. The natural log of E is just 1. And then what's going to be my last step? Dividing by 0.07. And this is probably a problem where, you could leave it as is if you want a precise answer. They might want you to get a decimal approximation, so that's when you want to break out a calculator. And you would type in the natural log, you should know how to type unlike me, of 10 divided by 0.07 gives you about 32.89 years. Which again, this just again illustrates how powerful compounding interest is, because 7% is like a pretty realistic return on a bank account. So effectively, by just putting in $1,000 and waiting 30 years, not doing anything with it, you now multiplied your investment by 10. You got $9,000 for literally doing nothing but being patient, which is how a retirement plan works. It's how investing works. Always check with somebody who actually knows what they're talking about, unlike me, to make sure you're making like a pretty safe investment. Don't just listen to some random dude on TikTok, but it helps a lot. It's a very, very powerful idea. So let's say you were wanting to kind of work backwards to figure out how much you needed to invest. So let's say you're like, okay, I found myself a great continuously compounding bank account with a 7% return, and I plan to just keep it in there for 40 years. I'm going to invest my money today, and I want to know getting $50,000 from it. So here, at time 0, I don't know my initial amount this time. This is what I'm actually solving for. And this might be something you actually sit down and do at some point. You're like, okay, I have my goal. How much do I need to invest? I know at the end of 40 years, I want $50,000 in there. So let's go ahead and start to plug in what it is we know. So we know our final amount we want is $50,000. We don't know how much we plan to invest yet. We know our rate of return is 7%, and we know we're going to invest it for 40 years. Now, what would I have to do in order to solve for that initial amount? Well, here, e to the 0.07 times 40, that is actually just a number. So we have a naught times a messy number. How do we get rid of timesing by a messy number? We divide by that messy number. That cancels out to make 1, and now this is something I can plug very carefully into a calculator. So let's go ahead and do that. So here, I want to plug in 50,000 divided by E to the 0.07 times 40. So if I invested $3,040.50, that would happen. Which I think is super cool, because in a comparative sense, I mean, that's $47,000 for, again, doing nothing, which is awesome. So I encourage you to, look into it. Think about your retirement early. It's a good idea. And the way that it works is exactly this math. This model is how you make money by doing very little other than just saving, but saving wisely in something that will give you some sort of return. If you just stick it in a savings account that has no real return to it, this isn't going to happen. You want to do your research to find something that will actually give you a good return. We can also do more interesting things with a discrete compound interest formula as well. By discrete, I mean it's no longer continuously compounding, but compounds a certain number of times per year, and that's that n. So let's take a look at an example of that. So it says, suppose you have $10,000 at the end of some amount of time after investing $1,000 in an investment account that compounds quarterly with a typical annual return of 7%. How much time would you need to wait? So let's sort of think it through this time. So we have kind of the amount at the end of time t, we have our starting principal, we have our rates, we have what time t is, and we have the number of times we compound per year. In the formula, that the ending amount is your principal times 1 plus r over n to the nt. So go ahead and pause your video and see if you can identify which piece of information would go where. So we have $10,000 at the end. We start with a principal of $1,000. We have 1 plus, we have a typical annual return of 7%. We don't know the amount of time, so that's going to stay as a t, and it compounds quarterly, so 4 times per year. And now we can solve for how much time we would need to wait in this situation. So in order to solve for t, eventually we're going to have to log both sides so that we can move that out front. But first we want to get the thing being exponentiated by itself. So first thing we want to do is divide by 1,000 on both sides. That cancels out to make 1, and then we're left with here 10 left. And then we have 1 plus 0.07 over 4 to the 4 times t. Now we want to go ahead and log both sides. You can pick a log of any base, just for simplicity. Since this is kind of a funky number, I'm just going to natural log both sides, but you can technically pick a log of any base. And the reason why we do that is that now moves the exponent out front. So we're left with the natural log of 10 is equal to 4 times t times the natural log of 1 plus 0.07 over 4. Now our last step to get t by itself is it's being multiplied by a whole bunch of funky things. So we want to divide by those whole bunch of funky things. Notice how this time this didn't cancel out because this doesn't have an e in it. It's going to make something other than 1. I have no idea what exactly it is, but it's going to be a number different than 1. That cancels out, that cancels out. I'm left with t, and then at this point, this is where you would want to break out a calculator and enter this in very carefully. So we have the natural log of 10 divided by 4 times the natural log of 1 plus 0.07 divided by 4 in parentheses, and then it looks like we'd have to wait about 33 years. And that's whenever our investment would grow by 10 times the amount. Which again, I mean, it's cool that it can grow without you actually having to do any physical labor. You just let it sit there and let the beauty of compound interest do its thing. There are also logistic growth models that you may come across, and the idea that is really nice about logistic growth is you can have this idea of a carrying capacity, so sort of in a maximum amount that it may grow to. So for example, it would kind of look a little bit like this, because oftentimes it's realistic that you may initially sort of grow exponentially, but then level off. And in particular, this is really how a lot of pandemics and how a lot of disease spread is modeled, because the reality is that if you're growing in a population, there's only so many people it could even physically go to. You know, if you're thinking about, the plague and there's 7 billion people in the world, you can't grow bigger than 7 billion people. It just doesn't physically work. So that's where this idea of a carrying capacity works in. So C is our carrying capacity. That's the maximum amount it can grow to. We have kind of a different formula for the initial value. If you ever want to take like an epidemiology class to kind of figure out why that's the initial value, there is like a mathematical proof behind it. It's just not really what the focus of this course is. And then we also have a constant that determines sort of what the rate of growth is. Again, this is what epidemiologists do. It's what people who study the growth of diseases and that sort of thing, they use this logistic growth model a lot because it's actually much more realistic to how things grow in a population, because again, it has this idea of a carrying capacity. So let's take a look at this example, and then here I'm just going to rewrite this formula because this is definitely not a formula you need to have memorized by any means. It would have to be given to you if you're going to use it. So suppose, for example, you have a community of 1,000 people. So that's telling you that 1,000 people tells you that's really that carrying capacity, because if you're in a community with 1,000 people, it can't physically spread to more than 1,000 people. And you have one person in the flu. So that's telling you that your starting point is that one person. And in particular, the starting point's not as directly in the problem as much. It's going to be this C over 1 plus A is equal to 1 to represent that starting point. Again, that just has to be information given to you. You're not expected in this course to just like know that. And we have a logistic growth constant of B is equal to 0.603. Well, we want to estimate the number of people in this community that will have the flu after 10 days. So in order to plug into this model, we know C, we know B, we know that the T they want us to plug in is 10, but we don't know A yet. But we thankfully have a formula so that we can solve for A. We know it's the C over 1 plus A has to equal 1, our starting point, and we know that C is 1,000. So we have 1,000 over 1 plus A is equal to 1. Then I can solve for A. In order to solve for A here, I want to get him outside the denominator, so I want to multiply both sides by that denominator. Cancels out to make 1. I'm left with 1,000 equals. We distribute the 1 to both of these, but that doesn't really do much. 1 times 1 is still 1. 1 times 1A is 1A. And then we subtract 1 from both sides to get rid of that adding 1, so A is equal to 999. So our entire model, if we now have that we have a C of 1,000, an A of 999, and a B of 0.603, that's exactly what we're going to plug into our generic model given to us. So we have the function evaluated at 10 would be 1,000 divided by 1 plus 999, plugging that in for A, e to the negative 0.603, and then we're plugging in 10 for T. And that's exactly what we would then just plug into a calculator. This would definitely not be something you'd be expected to calculate by hand. So we'd have 1,000, 1 plus 999, e to the, and I'm going to use parentheses for what this is being raised to, 0.603 times 10, negative 0.603 times 10, and that gives us 293 people, 0.85. So that would round up to about 294 people having the flu after 10 days. And that's again kind of what it physically looks like here, is on day 10 we would have about 294 cases of the flu. And this is again one of those just more realistic models. So a lot of times as you get deeper into math, there's been a lot of work that has been done to find these realistic models, to model the fact that at first he's only spreading it to a few people, but then you've got 5 people each spreading it to 10 people each. And then it really starts to, much more rapidly and exponentially grow. And then eventually, basically the whole town has the flu, and it's going to level off, because I physically can't have more than 1,000 people in town have the flu. And really, also according to this model, after about 21 days, the entire town would have the flu. So that's just kind of have it in the back of your mind that we really can model a lot of real-world phenomenon using these tools. Exponents and logs are used all the time to model these real-world phenomena. And I encourage you to look into epidemiology and statistics to kind of figure out how do we know these models work. It takes a lot of data collection and seeing, through math and also just some of the scientific process to see which of these models is really the best model for these real-world phenomena. And to really also emphasize a model is just that, it's a prediction. Life is a little bit messier. There are more variables than just time. Whenever we're talking about the spread of something like the flu. So they give you a good ballpark, but real life is going to have a little bit of a margin of error to that, which again, statistics and epidemiology look into a lot. So if this is the type of thing that interests you, definitely look into it.